number one, everyone's taking the exam, right? Can you step up for a second? Yeah. All right, so number one was about solving a double integral, and then I asked you, what's a valid interpretation of the value of your answer? Okay, so here's just another example. So let's do, so here, let's do the double integral here of negative sine x plus cosine y, dA, whatever, and that's over this square region, which is x and y from 2 to 6. So 2 to 6, 2 to 6. And that's the picture I'm showing here. I'm showing x and y from, no, what? 2 to 6. Negative 2? That's weird. Showing the whole thing. Does this change? No, not really what I wanted here. I'm going to do like 0. What I want is like 0 to 4. Okay, better. All right, that's good. Perfect. All right, so let me see if I can. There we go. That's a good one. All right, so negative sine x plus sine y, and I'm going from 0 to 4 and 0 to 4. Okay, and the first thing is that, so we talked about when you find the value of a v for value, okay, v for value of this is going to be a number, right? If you solve this out, you get a number. Is that right? And so the question number 2 was, if you solve it in a double integral and you're going to get a value, what's a valid interpretation of that number? Lots of you picked signed area. Okay, so that is just, that's like your cylinders were not firing, okay? Double integrals, we said it like in 4 or 5 different classes, and you had whole worksheets on what double integrals are about. So, in a word, what do double integrals have to do with? Volume, okay? Double integrals have to do with volume. We can trick them into getting us the area of a flat region if we do what? We make the function 1. But that was not the case here at all, right? So the function's not 1, it's some function, so it's going to be a wavy surface. So then double integral can only be about something about volume, okay? It's not about area. It's not about area. We said it many, many, many times. I guess the word signed, you just read the word signed and you picked that one, maybe. But you have to read everything. It said the next word was area, okay? And double integrals are not about area. They're about volume in R3, right? Volume. Okay, but they're not equal to volume, right? This is a bad choice. A. Okay. So what do we say? They're about, so it's not volume because you have places where surfaces can go underneath the xy plane. Remember talking about this? And what happens? What does the double integral do when the surface goes below the xy plane? It subtracts those volumes, right? So volumes are always positive. So how many solids does this integral create? Do you see how many it creates? 4, right? It creates 4 solids, 2 of which are above. No, all volumes are positive. So solids. So 2 of those solids are above. So like there's one here, right? So I'll call it, say, S1. And there's one up here, call that S2. And then there's one down here, call that S3. And then one back over here, call that S4. And each of those solids has a volume, and volume is always positive. Volume is always a positive number. There's no such thing as negative volume. But integrals, when your function value is negative, right? Let's think of rate of change. If that's negative, then when you accumulate, you're going to get a negative value. But geometrically, areas and volumes are always positive things. All right, so if the volumes of these are V1, V2, V3, and V4 respectively, then how could you write what this integral, what A equals in terms of the volumes V1, V2, V3, and V4? What would it be? What expression would you write for those 4 volumes of those solids that would give you the value of A?
S1 plus S2 minus S3 minus 4.
Yeah, so it would be V1 plus V2 minus V3 minus V4. Any solid that's carved out below the XY plane, that volume, the value of that volume will be a negative contribution to the integral, but the volume's still positive, right? So this is what signed volume means. This is what signed volume means. Okay, and so one of the choices, signed volume was not a choice, but choice D was difference of volumes. So the question is that a valid interpretation of signed volume or not? Sure. Yeah, so and in fact that's kind of explaining what signed volume is, right? It's explaining what signed volume is. You have all the volumes that are above, and those are added, and then all the volumes below get subtracted. So difference of volumes, right? Difference of volumes. Okay, so I'm crediting anyone who put D or E. If you put none of the above, I'm giving you credit, because I guess I didn't explain that well enough, and lots of people understood that it was signed volume, but didn't choose D for whatever reason, okay? So if you chose D or E, you got credit for this. If you chose B, signed area, you do not get credit, okay? So something went wrong in your studying, okay? Because signed area of a vertical surface, that was line integral.Maybe it's because we did it the day before the test. But it wasn't a double integral, and double integrals never meant area, okay? Except if Z equals 1. Okay, yeah. So signed area of a vertical surface, that's line integrals. That's the new stuff. Okay. Any questions on that? Okay, can someone go get... Kenneth. Questions on what double integrals mean? Okay, so we are working on line integrals. Let's just review, if I can find that. Is it in this? I don't think it's in this. Let's see here. There it is. Yes. Okay, so let's just review this real quick. We said line integrals were of this form, right? And we said, what is fxy? What is c? What is ds? Fx, and what was fxy? What does that represent? Multivariable function, real valued multivariable function, which gives us a surface. And then c is? Right, a curve over which we're going to integrate that surface, and then ds was a little bit of arc length of c. So ds dt, the rate of change of the length of c for a small change in t. We said that was what? Magnitude of velocity, or the first derivative of our vector function, right? So that's like speed. So that's like this. And then so ds, we found that it was ds, and this allowed us to write the integral, right? So to do a single integral, we can only have a single variable. But fxy, multivariable function. So then we get our curve in terms of t, and then we rewrite. So once we have that curve parameterized in terms of t, then we rewrite the function in terms of t, and then we have our ds, which is the derivative magnitude dt. And I think we were able to finish an example last time, right? Did we do a first example of that? Okay, so let's do another example. Save that. All right. Okay, so the height of a roof of a building is modeled by this gold, yellow function. I'm just showing in the first for x and y greater than 0. So 10 minus 1/8 x squared minus 1/12 y squared is modeling some roof, some architecturally interesting building. And the wall then is the gray, and that's modeled by 2x plus y equals 8 in the first quadrant. So I'm showing more than what it would actually be built as. So let's, all right, let me give you a chance to jot all that down. Okay, there we go. So here's our situation. And so let me outline what we're talking about here. So the actual wall, then the ground is XY, the XY plane. And then we're talking about in the first quadrant. And then the roof is like this. So this is our wall. Make sense? So we need to find the area of that wall. We want to find the area of that wall. How are we going to do it? So if we think about it, we know that single integrals can give us area or signed area. And so it's like we're integrating what? We're integrating this surface over what? We're integrating this gold surface over yeah, this little segment, right? So that's our C. This segment down here is our C. From there to there. Oh, shoot. There we go. Okay. And we're going to integrate what? This surface over that line C. And if we do that, that's going to accumulate all this area here, right? Okay, so what do we need to do that? So we know we're going to be doing the integral of fxy ds over C. And so being able to solve that integral means doing what? Solving an integral like that? What's that? Finding the curve so that we can, what do we need to do to this integral? Yeah, we need to get everything, we need to rewrite this integral in terms of one variable, which would be our parameter t, and that parameter t was going to be the parameter t that will enable us to, or will write this curve c. So we need to write c, what, as a vector function, right? A single variable vector function. And that's going to have how many components? This one will have 2 because it lives in the xy plane, right? And so, I think you can try to, you have enough from last time and from the setup today, you try to work on this. So you're going to write that vector function, and then you're going to change fxy in terms of t and ds in terms of t. And it's all based on the vector function you came up with for that segment C. So give it a shot. If you don't know what to do, then get some help. So we need to parameterize that curve. This is actually a straight line, but string of points is called a curve, whether it's straight or not. Okay, so this curve C, parameterizing this curve. Everyone making progress on that? Some nods. Joseph, what'd you get?
For the x parameter, I got 8 minus t over 2.
Okay.
And I got t for the y parameters.
All right, so you use t for y, and then 8 minus, so y.
8 minus t over 2.
You solve for x, 8 minus t over 2. Okay, so that's a valid way of doing it. So there's lots of ways of doing this, but I'm guessing probably most people didn't make ty, so yeah, we could totally do it that way. Did anyone do it a different way?
Yeah, t and then 8 minus 2t.
So t and 8 minus 2t? It avoids a fraction, but it's perfectly legit what you did. All right? Okay, so we got that. And so then from there, we can set up our integral. So then the question is, what does t go from? From what to what? So this is our x and our y. So we need t1, or I guess we could do this as t1. This is a lower value of x. So we can do t1 here, t2 here. So what is t1?
0.
And that's x equals 0, right? That's the y-intercept. And then t2 is when y equals 0. So is that 4? So we do the integral from 0 to 4, t1. Now, if you had a different parameterization, like Joseph, then these will be different, right? So that if he had y equals t, so he might go from like 0 to, what would this be? 8?
I think it was 8.
Yeah, so you'd have 0 to 8 if you did the way you did it, because it's got to match up with your parameterization. Okay, so then what's f of xy going to be? So it's going to be, let's see, Ryan.
I had 10 minus t squared over 8
Okay.
minus the quantity of negative 2t plus 8 squared divided by 12.
Good.
And then I had that entire function
Right.
multiplied by the magnitude of the derivative of the position motion.
Good. So that is
Radical 5.
1 minus 2. So the magnitude of that you should have gotten was
Radical 5.
radical 5. So then times radical 5 dt. Did you have that or something close? 1, 2 nods. Any questions on that? Follow it? So this is our fxy written in terms of t, because x is t and y is 8 minus 2t. And then we have our r, magnitude of r prime, this is our ds, right? This is our ds. Okay, so we could do the algebra. That's more that we don't want to take the time in class, but just so we can get a number and talk about area a little bit, I guess. Let's see. Is that here? Nope. Where is it? Here, maybe? Yeah. So let's just put that in quick and get an answer. So integral from 0 to 4 of 10 minus t squared by 8 minus 8 minus 2t squared divided by 12, and that times 5 dt. 67.6 square units. Okay, questions on that? So that's the area of that wall, 67 units. If that function ever goes below the xy plane, where the curve, over for some values of that, or some points of that curve, what happens to those areas then? They get subtracted. Any areas that go below the xy plane, those are still positive areas, but those will get subtracted out from the areas that are above the xy plane along C. We're only talking about along C, right? Okay, questions on this example? Okay, so then we have, so that's line integrals of multivariable functions, okay? Line integrals of multivariable functions. Okay, so then there's line integrals of vector fields. And the most common example of that so if the most common example of that is if you have a come learn some calculus. All right, so if this were a force field, right? So a force field is an example of a vector field, right? Given any point, say in the plane, there's an associated force with it, and forces we know are modeled by vectors. Okay, so if we had a force field, let's put that as a force field. Okay, and so that force field is applying forces to whatever's in it, right? It applies a force to whatever's in it, and at any given location, it's applying a particular force, which was the vector at that place. So if we had some, say, starting point, and say it was a car, okay, and we're going to drive through the force field like this. Okay? We're going to drive from there to there along that path, see? All right, and that's defined by our so the force field is not moving our car, okay? Our car is moved by the engine and the steering wheel, okay? But as we go through this, forces are being applied to the car, okay? So forces are being applied to the car as we go through this force field, okay? So at any given point here, so let's say right about here, looking at the vectors that are shown, right? If we showed all the vectors, what would it look like? If we showed all the vectors in this field, what would we see? It'd just be blue, right? It'd just be a big blue block, okay? But based on the vectors that were shown here, what is the vector say at that point right there? Maybe like this? Is that fair? Right, so based on the vectors around there, I can kind of guess maybe that the force on the car, we're heading this way down on our path, but the force on the car is like this. So maybe this is like wind, right? So this is kind of like we're driving along the street, and the motor and the steering wheel and our skill is keeping us on the street, but then there's there's wind forces on the car, right? Okay, so there's a wind force right there. And so as we move a little bit, there's going to be a little force on the car, right? And so we change our distance a little bit, and there's this force. And so what does the force field do on the car then? As we move, and there's force being applied along this distance. So when force is applied on a distance, work, right? So the force field does work. But what's kind of weird here is what you think is that the force field is resulting in the path, right? But that's not the case. It's doing work on the car, but there's other forces too, that the forces in the car that are keeping it on the path. Does that make sense? So you got to kind of, it's not that the wind is pushing us on this path, right? Because clearly it's not. Because we're going this way, clearly if they just let the wind blow us like a piece of paper, it would be blowing us this way. Okay, so the little bit of work that we do for a little bit of distance is, so this is the force field. Okay, and so the force field is a vector field of position, right? It's a function of position. And so we have each component is a function of position. Okay, so we have the work and then our little change in position. I'll do that in red because it's hard to see. So we have a little change in position that's like a little dr, right? So that's supposed to be a little vector right there. And so how do we calculate for that little change in r, that little vector, that little change in r vector right there? It's like tangent to the curve and a very, minuscule distance. How do we calculate the work that the force field does for that little change in distance right there? So what is the amount of work, or the little bit of work that the force field does for that little change in distance and the force at that point? What would it be? How do we remember how we calculate work? So is it dot product or cross product? What does dot product do? It tells us the product of the magnitudes, what? In as much as they are same direction. Cross product, the magnitude of the cross product is product of the magnitudes as much as they are orthogonal. So which do we want for work? Yeah, we want to know dot product. We want to know how much of that force is in that direction, right? How much of that force is in the direction that we're going. That's the amount of work that the field is doing at that point. So it's going to be dot product. So we're going to have F dot dr. We want the amount of that blue force in the direction of the little red dr vector. And that product of those magnitudes will get us how much work, right? Because the amount of the force in this direction is doing no work on the car, if the car's moving that way. Only the component of that force in the direction of motion is actually doing work on the car. So it's kind of like that component of that vector is like helping the engine to work a little less, right? Okay, so then we want to do what? So we want to accumulate all the little bits of work over C to get the total. The total work done by the force field on the car as the car drives this road. And so that's going to be F dot dr. Okay. So if R is then defined as what? X of t, y of t, okay. And what is dr dt? Piece of cake, right? What's the derivative of the vector function? Just like falling out of bed, exactly what you'd hope and want to do. dx dt, dy dt, right? You just take the individual derivatives. So then what would dr be? That whole thing, that thing, times dt. Yeah, but these are functions of t. We can't. This is a function. These are functions of t. So we need dx dt, dy dt. Okay, so we're going to take our force field and we're going to write it in terms of t. So the force field would be in terms of x and y, but we got just like before in the other. We're going to write this in terms of t. Get in terms of t. And then our dr is going to be the vector dx dt, dy dt, and then dt. And then when we do that dot product, we'll have just a single variable function of t, and we can solve the single integral. And of course, c will integrate from the starting value of t, so t1 to t2, just like before. So there's a lot of similarities to the multivariable line integral. Now it's a vector. Now we're integrating our line integrals for a vector function, which is is a vector field. So we have the vector field, and then we have the parameterization of the curve, and that's what gives us all the relationships of t that we will do. Okay, so let's talk about whether the work is positive or negative. So let's look at this first example here. Do you think that whenever the force field is helping the car, reducing the workload of the car, so then the workload of the car is going down, that means that the work that the force field is doing is positive, right? Because it's positive. And whenever the work is working against the car and making the car's work go up, then that's negative work that the force field is doing. Does that make sense? So what is this for this path that I drew? What do you think? Is the overall work done by the force field, is it positive or negative on the car here? Positive, because at the beginning it's kind of close to zero, right? It's like we're kind of heading perpendicular to the forces. So the work is like zero. And then through here, the force field helping or hurting? Helping. It's reducing the workload of the car, so therefore it's contributing positive work to the car, and then it's positive this whole way. All right. So what about another example? C2. From there to there. T1 to T2. Work for the work that the vector field does.
0.
I'm trying to draw 0, so it's like in spirit, it's about 0, right? And then if we did this, T1, how about that? C3. Negative or positive? But some of it's positive, right? But most of it's negative, right? So it's this idea of an integral is you have negative and positive contributions in an integral. So you just have to eyeball it, and you would say, there's a lot of negative work being done here. The wind is pushing against the car. It's making the car do more work. So this is negative work done by the force field, and then it's helping at the end. Now, if these vectors were all very, very small, and then these vectors were really, really big, then that would be positive work, right? That'd be positive work. So there's distance and there's the magnitude of the vectors are both coming into play here. Does it make sense? So this last one would be the work is less than 0. This red one was work about 0. And the first one I drew was positive. 0 through here, but then all positive components through there. All right, so let's do an example. Questions on now they don't all have to be force fields, but that's like the most common and most it's the example that makes the most sense or the most prevalent example, I should say, in a real world setting is that you're moving through a force field and the the line integral of the vector field is giving you the work done by the force field. That's the most common example. But we can work these examples, and when they have nothing to do with work, right? So the mechanics of solving the integral and setting it up, this could be just any vector field, okay? It doesn't have to be a force field. Solving it's the same. Okay, let's do this one. I wrote this down somewhere. Okay, so okay, so this is the force field, and we want to find the line integral if C is the part of the circle radius 2 centered at the origin from -2, 0 to -2, 0. And that's what that looks like. So there's that vector field. And so before we do this, can we kind of try to predict if this is going to be negative, close to 0, or positive, right? So can we look at this and kind of maybe predict what do we expect for the final answer? Here's some positives and some negatives. I should say counterclockwise. So what about the beginning here? So we would say large negative, small negative, 0, small positive, large positive at the beginning here. Contribution. Small negative, right? We're going against the grain, right? So we're going against the vector field means negative value of the line integral. So this would be kind of like a small negative. What about through here? 0. And then what about the end? More negative, right? The more negative contribution. So there really is not any distinct positive or prevalent positive contribution. It's like small negative contribution through here, then 0 through there, and then again at the end, very end is negative again. So we're expecting a negative value for this. So what's the key? So we want to we need to figure out what this is. And what's the whole key to setting this up to solve it? What's that? And what does that mean, converting it in terms of t? What do we have to do? Yeah.
Parameterize the curve.
Yeah, we're going to parameterize the curve. We're going to get it as a vector function of one variable t. So that is most of the deal here. And then we're just going to use that. So you got to remember, we've done this before. We've parameterized curves. We've written vector functions, and we had this three-ish techniques for doing this. And we had to use whatever technique applies in the situation. So what are we going to do for this one? Set x equal to t? Anybody remember? Yeah, Andrew.
No, do it with cosine and sine.
Mm-hmm.
So
Yeah.
set x squared is cosine.
Yep. So x is cosine t. And y sine t. Is that right?
The radius
Okay? Over 2. So if we want the x-coordinate to be 2 when t equals 0, we're going to do times, right? Does that work for our parameterization? Remember doing that? Remember whenever we had circles, we were parameterizing curves, whenever we had circles, we wanted to take advantage of cosine and sine. Because it gets ugly. If you try to set x equals t, then you got ugliness. Square roots, arc sine, arc cosine, we want to avoid that. Okay, so can you take it from there? Can we set this up? So here, this is our vector. This is our vector field, right? This is our vector field, F. This is the x and y components of the vector field. So we need, now that we've got the curve parameterized in terms of t, we're rewriting the general form of the line integral all in terms of t now. Did I do it right? Did I do it right? I got 1 thumbs up. So what do? You write down the vector field in terms of t, x, y, 1 minus x, right? And then you got your dx dt, dy dt, and then dot product, right? Sum of the products of the corresponding components, right? So that'd be -8 cosine squared, and then sine squared, and then 2 cosine t times that. So while you're studying that, I'm going to put in that integral, and we just want to see that it's negative. That's what we want. It wants to be negative. So, any questions? Do you follow it? Oh, and then from what to what? 0 to pi, right? Because t is going to be 0 at the 2, 0, it's pi. -8. This as fast as I can. Any questions while I'm putting this in? That's sine squared though, right? Ask. If you're not sure, ask. Do I have it right now? Expecting negative. Got it. Actually, it turned out to be -2 pi, right? So it turned out to be -2 pi.